today we're going to mostly go over k-nearest neighbors and identification trees, which are 2 of the 3 topics on the quiz on Wednesday. And then constraint satisfaction problems are also on the quiz, but we talked about those 2 weeks ago, so we probably won't have time for them today. So before we go into nearest neighbors and identification trees, the big picture of what we're doing here is supervised machine learning. So the first half of 6034 up through constraint propagation was about tree-based AI methods. So things like games, search, rule-based systems, and constraint propagation. But the remainder of 6034 is going to be mostly supervised machine learning. So I'm going to define what that is. And then we'll look at 2 methods for doing supervised machine learning. So the general idea is you have a bunch of training points. And these could be things like people who are known to be vampires or not vampires in the classroom example. So these are training points or training data. And each of these points has a bunch of features. So just to make this generic, we'll say that the features are x1, x2, x3, and so on. And these could be things like whether or not they eat garlic, whether or not they cast a shadow, how tall they are. So these guys are features. And then each of these points has some known classification that we'll call y. The classification could be Boolean, like you're either a vampire or you're not a vampire. It could also be discrete. So for example, if you're classifying someone as a Democrat, a Republican, or an independent, then there are more than 2 categories. Or it could be continuous. Like if you wanted to classify someone by, say, predicting how tall they are based on some information that you know about them. So all of these training points have known features and known classifications. So all that information is given. And then the objective is we have some unknown point that has a bunch of known features, but we don't know its classification. So the overall goal of supervised machine learning is to figure out that point's classification. So we could say that the supervised machine learning objective is given all of this training data to come up with some model or rule for classifying unknown points. So given some training data, with known features, which are these x sub I, and known classifications, we're going to produce some rule for classifying new points. These new points also have known features. But they have unknown classification. So that's the general idea of machine learning. And so now we'll look at 2 specific ways of producing a rule for classifying points, which are nearest neighbors and identification trees. So first, nearest neighbors. Let's take a really simple example. Let's say that we have 3 points. These are our training points. 2 of them have class A, and 1 of them has class B. And they have some features, x1 and x2. And now we want to classify some unknown point. So let's say that our unknown point is, right here. How would we classify that using k equals 1, so looking at its one nearest neighbor?
We classify it as A?
Yeah.
Just A?
Yeah, we would classify it as A because k equals 1 means that we're just looking at this one nearest neighbor. What about k equals 2? We can't really tell because it's two nearest neighbors. One of them's an A and the other one's a B, so that's going to be a tie. So we don't actually care which one's closer. We just care about who the two nearest neighbors are. So we're going to say that's a tie, and we just can't tell what that point's classification is with two nearest neighbors. And then what about with three nearest neighbors? A again, because these 3 points are its three nearest neighbors, and 2 of them are A. So if k equals 3, it'll be A. So one thing we might want to do is for one nearest neighbor, or for any value of k, we might want boundary lines in the space that tell us how a point is classified so that we don't have to figure out who its neighbors are at every point. So we're going to try doing this with one nearest neighbors. So we'll draw boundaries for one nearest neighbors. So we'll take these 3 points again. And now we want to figure out how we can draw lines in this space to divide it up so that on one side of the line you're an A and on the other side of the line you're a B. And we might end up with more than just 2 regions. But the way we're going to do this is we'll start by imagining that there are lines between every pair of points that are different classes. So there's a line between this A and B and a line between that A and B. And then we'll take the perpendicular bisector of each of those lines. So we get this and that. And so this line tells us that if we're right on the line, we're equidistant from the A and the B, and we don't know what our classification is with one nearest neighbor because we're equally close to them. But if you move a little bit to one side of the line, you become a B, and if you move a little bit to the other side, you become an A. And so similarly with this line. And then the question is just where these two lines meet. So in this case, it's fairly straightforward. We can just extend the lines until they meet, and they'll meet right about there. But in more complicated situations, it's helpful to notice that this point right here has a special property, that it's equidistant from the two A's and the B. So another way of saying that is it's the center of the circle defined by these 3 points, because every point on a circle is equidistant from the center. So this is the point where if you move a little bit in one direction, you get closest to this B. If you move a little bit another way, you're closest to that A. And if you move the other way, you're closest to this A. So let's try that on a more complicated example. So over here we have the rocks problem from the 2008 final, which is on a handout over there. And we're going to try drawing in the boundaries to divide up this space using one nearest neighbor. So what would we do first? How do we draw boundaries on this? Yeah.
Draw lines from different nodes.
Yeah. So we'll imagine that there are lines between all the points that are different classes. So we'll get those guys, and that SI pair. We have a bunch of ways that we can pair up the S's and M's over here. And then we have an M and an I, and another M and an I. Oh, and then we have that MI. There are some lines, we could draw in all the lines, like you could connect this S to that I, but it turns out that line isn't going to matter because there's a lot of stuff happening in between. So now we'll take the perpendicular bisector of each of those. And up on this corner, it'll be fairly easy because there's nothing else going on. So this line can just go off to infinity. So when you're drawing these lines, make sure you draw them all the way off the graph or put arrows to show they go to infinity, because otherwise we'll end up with some region over here where the classification is just undefined. And then over here, we could put one in for the S and the M. That goes off to infinity. But then there's going to be some more complicated regions. So what's going to happen up in here? We have this diagonal line and this vertical line. Where do they meet? Yeah, it's going to be where we're equidistant from this S, and this I. So it'll be right here. So what that means is this vertical line doesn't actually take effect unless we're below the SI line. And another way of thinking about that is if we put in a test point, say right here, how should that point be classified with one nearest neighbor? S, because it's closer to that. So if we had put in the vertical line, it would get misclassified as an I. So we want it to be classified using that S. So then we can extend this one down, and this one goes outward like that for some amount of time. What do we do with this horizontal line and that stuff? Yeah, it looks like we can just draw that across. And that makes sense because this point right here is where we're equidistant from the S, the I, and the M. So that's where those three lines meet. This one's going to just go all the way across because if you test any point on either side of it, you end up being closer to one of the S's or closer to one of the M's. Down here we have this thing. It turns out there is also this line, but it's not going to take effect until we're like somewhere down there, so we don't have to worry about it. Because what happens at some point out here, the line is defined by those 2 points instead of those two. But we don't actually have to worry about that because it's off the graph. So then the question is just what happens over here. So it turns out in all of this region, we're going to be closer to this M and this I than to that I. So we can actually ignore that line. And this is just going to go like that. So now we have boundaries that divide up the space. So if we wanted to put in a test point like over here, instead of worrying about who its one closest neighbor is, we can just say, oh, it's in the I region. So that means it's going to be classified as I. And we don't care whether it's closer to this I or that I. So in theory, you could also do this for higher values of k, but it's rather non-intuitive because it's hard to picture the boundaries. So we'll only ever ask you to do it for one nearest neighbor. OK, so then we talked about different values of k. So then there's the question, why would you want one value of k over another? So let's take a look at an example where it makes a difference what value of k you have. So we'll go back to having A's and B's. Let's say that we have some training data where we have a bunch of A's over on the left side and some B's over on the right side. And then we have this one B that's over on the left side that looks like a bit of an outlier. So if we had some test point, say, right over here, how do you think we want that to be classified? A or B? A, because it's over on the left side where most of the A's are. But how would it be classified with one nearest neighbor? B, because it's closest to that B. So if k equals 1, we would get B. And that's called overfitting. So in this case, k equals 1 is overfitting. And overfitting is basically when you're relying overly much on your data. So you're assuming that even small fluctuations in the data are significant. And as a result, you end up building a classifier that puts things that are in this little region, it says that they're B, even though really you would want to smooth over that outlier in the data. So we could try some value like k equals 3. How would the blue point be classified with k equals 3? A, because 2 of its nearest neighbors are A, and another one is B, so the A's win. So with k equals 3, it would be an A, and it seems like that's what we want because this point is generally in the A region. So that seems like a reasonable value in this case. Let's see if it also, let's see what happens if we do, say, k equals 11. How would that blue point be classified with k equals 11? There are 11 points total.
Still A?
Yeah, still A. But that's just because, that's not actually because it's over here. That's just because there are more A's in our data than B's. So with k equals 11, we're looking at everything. And it's classified as A. But then the problem is, I mean, that seems OK for the blue point. But what happens if we have some orange point way over here, and we classify it with k equals 11? What do we get? Still A. And that's just because our data happens to have more A's than B's. So that's kind of silly. So k equals 11 in this case is what's called underfitting, which is just the opposite of overfitting. Instead of depending too much on the regularity in the data, we're smoothing over it too much. So we're not relying enough on our data. And as a result, we're ignoring differences in the data that should be real trends. So k equals 1 and k equals 11 are both values of k that wouldn't work very well, but for different reasons. So now we might ask, how do we find a good value of k? So that's when this thing called cross-validation comes in. And cross-validation is a way of figuring out whether you have a good parameter such as k. And it's sort of like what we just did with the blue point, but instead of using our intuition and saying, I think this blue point should be an A, you use a real data point. So for example, we might take this A and pretend that it's not part of the data, and then choose some value of k, like k equals 1, and then we'll see, is this point classified correctly using k equals 1? And so in this case, we would say, no, it's closer to the B than to the A, so k equals 1 causes that to be misclassified. Whereas k equals 3, it gets correctly classified as an A. So the general idea of cross-validation is we're going to set aside part of our training data and use it as test data. And we can use that to figure out whether we have good parameters. So we'll set aside part of the training data. Then we'll train using the remaining data. In this case, training just means choosing a value of k. And then we'll test whether the data that we set aside gets classified correctly. So there are many ways to do cross-validation. You can do leave one out where you just take out one point at a time. You could also take out like a third of the data and test whether it gets classified correctly. But the general idea is that helps you figure out whether the parameters make sense. So another parameter that we have control over in k-nearest neighbors is the distance metric. So far we've just been using Euclidean distance, which is the straight line distance between 2 points. But in some cases, we might want to use different distance metrics. So we'll start by putting up the formula for Euclidean distance just so that we can compare the other metrics to it. So the Euclidean distance between two vectors u and v, where these are just points that could be two-dimensional, like what we've been looking at, or multi-dimensional, is going to be the square root of the sum over each component of the vectors of the difference between those components squared. So for example, if we have some point u and some other point v, then that's just going to give us this straight line distance. So then another similar distance metric is Hamming distance. Actually, we'll do Manhattan distance first. Manhattan distance is also known as taxicab distance. And the idea is in the city of Manhattan, all the streets are either north-south or east-west. So if you want to get from some point U over here to some point V over there, you can't go straight there. You have to go along the streets. So you would have to do something like that, and that would be the Hamming distance between U and V. Sorry, the Manhattan distance between U and V. So the formula for that also sums over all of the components, but it's just going to take the absolute value between each component. So it's the change in the x direction and the change in the y direction in this case. And a case when you might want to use that is if you were classifying people based on what grocery store they lived closest to, maybe for advertising purposes. Then you don't care which grocery store has the shortest Euclidean distance then, because they can't get there by going through the blocks. They have to go along the streets. So effectively the closest would be using Manhattan distance. And then we have Hamming distance. Hamming distance is useful if you want to compare symbolic things, because it just looks at whether the vector components are the same or not. So it'll be the sum over all of the components and just asking whether they're different or not. So an example would be maybe we want to compare some children's toys where we have one toy U, which is triangular and red and soft. And so we obviously can't use Euclidean distance for this because there are no numbers. And then we have some other toy that's triangular and blue and soft. Then what would be the Hamming distance between these two toys? How many components are different? Just one. So what we're doing is we're looking at each component and we're saying that one's not different, that one is different, and that one's not different. So we would get a Hamming distance of 1. And you could do the same thing with numeric points, just looking at each component of the vector and seeing is it the same or is it different. And then finally we have cosine distance, which is going to look at the angle between 2 points. So for example, if we have some vector u and some vector v, it'll look at this angle. And the thing is, cosine is a similarity metric, so the cosine of a smaller angle is actually a bigger number, so we're just going to negate it and 1 minus the cosine so that it's effectively larger angles mean larger distance. So the formula for that will be the distance is equal to 1 minus the cosine of the angle between the vectors. And the cosine of the angle will just be the dot product of the vectors divided by the distance, the lengths of the vectors. So an example of when you might want to use this is if you care more about the ratio between the features than the actual quantities. So if you were looking at something like recipes that have flour and sugar, then because you can scale a recipe, it doesn't actually matter how much sugar there is. It just matters how much sugar there is in proportion to how much flour. So if you had a bunch of recipes over there and a bunch over here, you would want to look at the angles between recipes rather than the actual Euclidean distance between them. Another neat real-world example is if you were trying to cluster stars into galaxies based on which part of the sky they were in. And then one final thing we can do, which isn't actually a distance metric, is we could transform to polar coordinates. So the basic idea there is if you have some data that looks sort of concentric or angular like this, then you can just transform it so that instead of graphing x and y, you could graph the radius and the angle, and then you would get two nice straight lines of points like that. So that can make the data easier to work with. And so distance metrics are another thing that we can confirm using cross-validation. You can choose some distance metric, try classifying points, and use cross-validation to figure out whether it's a good metric. Are there any questions on this so far? Okay, so one last thing with nearest neighbors is working backward, which is a good question on 2012 quiz 2, but for now we'll just look at a shorter question. So the idea here is that someone has classified a bunch of points using k-nearest neighbors and then erased the values of the classifications of the training data. And now we're trying to figure out what was the training data. So we're working backward from the classifications. So for example, let's say that we have 5 training points, but we don't know their classifications anymore. And then we have some test point over here. And we're told that with one nearest neighbor, it's classified as x. With 3 nearest neighbors, it's classified as y. And with 5 nearest neighbors, it's classified as x. So what does this tell us about our original training data? What do we know based on the fact that with one nearest neighbor, it's x? Yeah. Yeah, so that tells us that at this point 2 will have to be an x, because one nearest neighbor is looking at that, and with k equals 1, we said it was x. And so then what can we figure out about 3 nearest neighbors being y?
1, 3, or 1?
Yeah, so 1 and 3 have to be y because its 3 nearest neighbors are 1, 2, and 3. And when we consider all of those, we want it to be classified as y, so the majority have to be y. And then what do we know about 4 and 5? Yeah, both x. Because that's the only way that this point will be classified as x with 5 nearest neighbors. So that's the general idea of working backward to figure out the training data. Okay, so we're going to go on to identification trees now. So we're going to come back to the question of how to classify points with ID trees, also known as identification trees. And we'll start with the example with identifying trees from, I think, 2014 quiz 2. So the first thing we want to do to build an identification tree is to figure out how each of the feature tests or classifiers partitions the data. So here we have 4 feature tests. We have has leaves, orange foliage, leaf shape, and bark texture. So these are the different features that our test points have, and we want to see how they'll partition the data. So I'm going to come back to has leaves, because there's something unusual about it, but we'll start with orange foliage. So orange foliage can either be yes or no. So we'll draw 2 branches, one for yes and one for no. And then under the yes branch, we have 3 of our training points. We have 1 oak and 2 maples. And under the no branch, we have 2 oaks and 1 maple. So some things that are going on here. This thing is a classifier or feature test. Each of these things is a branch. And then each of these guys is a training point. So then we can look at another test. We have leaf shape. How many branches does the leaf shape test have? What are the possible leaf shapes? Pointy and rounded. So we'll have 2 branches there. Pointy or rounded. And it looks like pointy is almost all of the points. So we have 2 oaks and 3 maples there. And rounded is going to be just this 1 oak. And then we have bark texture. How many branches does bark texture have? 3. So we have glossy, furrowed, and smooth. And then it looks like we have 1 oak is glossy, 2 maples are smooth, and the remaining 3 trees are furrowed bark. What about has leaves? How many branches does that have? 1, because all of these trees have leaves, so we only have a yes branch. Will we ever want to use that test? No, because it doesn't actually separate our data at all, so that's not useful. But we'll put it in here anyway, just to see what happens. So now the next thing we want to do is calculate the disorder of these tests so that we have some measure of how good the test is. Because we already know intuitively this test isn't very good, but we want a numerical way of figuring that out. So we saw the formulas for disorder in lecture. I'll go over those again. So first we have the disorder of a branch. So to calculate the disorder of a branch, we're going to sum over all of the possible classifications. So in this case, oak and maple. So we'll say the sum over all classifications, y. And for each classification, we're going to take the fraction of points that have that classification and divide it by the total number of points in the branch. And then we'll take the log base 2 of that same fraction. And we're going to negate this formula because the log of a fraction ends up being negative, and we want disorder to be a positive number. So we'll just put a minus sign in front of that sum. So now let's try using that to calculate the disorder of some of these branches. So we can start with this one, which we already said is not a very good test. So should it have a high disorder or a low disorder? High disorder, because disorder is how disorderly something is or how mixed together it is. So let's see what happens. So we have, how many classifications do we have? 2. We have oak and maple. So we'll start with oak, and we'll look at the number of points that are oak over the total number of points in this branch. So we'll have 3 out of 6 times the log base 2 of that same fraction. And then we look at maples. That's also going to be 3 of them are maples out of 6 in the branch times the log of that same fraction. And we'll add those together and negate it. What's the log of 1/2? The log base 2 of 1/2? -1. So this is going to be negative 1/2 times -1 plus 1/2 times -1. And that just comes out to +1. So 1 is what you get if you have 2 classes and you have equal numbers of both, which is very high disorder. So that has a disorder of 1. And then what happens? What about here where we have 1 oak and 2 maples? How many classes do we have? 2 still. So we'll just figure out what fraction of these points are oaks. 1/3. So we have 1/3 log 1/3 plus 2/3 for the maples, log 2/3, and we'll negate that. And then this handy table of logs at the bottom of the sheet says that comes out to about 0.9. So we'll put that up here, 0.9. Do we know the disorder of this oak maple? 0.9. It's going to be the same thing where we have 1/3 of one and 2/3 of the other. And then similarly over here, this oak maple will be 0.9. And then here we have 2/5 and 3/5, so we could look that up in the table of logs. That thing is negative 2/5 log 2/5, because that's the fraction of oaks, plus 3/5 log 3/5. It's a fraction of maples. What does that come out to? 0.87. It says that in the table. So we'll put 0.87 there. What's the disorder if they're all the same? 0.97? Yes. Table reading. Okay. What's the disorder if they're all the same? 0. And if you work out the formula, you'll see that it does come out to 0. So that's 0, and that's 0. So now we have the disorder of each branch, and now we just need to know how to combine them together. So I'll go back here, and now we need the average test disorder. So average test disorder will just be a weighted average of all of the branches. So we're going to sum over all of the branches. So for each branch B, we'll take the fraction of points in that branch times the disorder of that branch. So the number of points in the branch times the number of points total. And we'll multiply that by the disorder of the branch B. So in this case, there's only one branch, so it's just going to be 1 is our overall disorder. For our orange foliage test, what fraction of the points are in the yes branch? Half, because we have 3 points here and 3 points there. So we could say 3/6 or 1/2, and then the same thing on the other side. So we add those up and get an overall disorder for this test of 0.9. And then for leaf shape, what fraction are in the pointy branch? 5/6. So we'll have 5 over 6 times 0.97 plus 1/6 times 0. And I think that comes out to somewhere around 0.84 maybe. You can check that later. And then for bark texture, we have 1/6 of the points in this glossy branch plus 3/6 or 1/2 of the points in the middle branch plus 2/6 of the points in the right branch. So we get an overall disorder of 0.45. So now we can ask which of these tests has the lowest disorder? Bark texture, because it has 0.45 and the others are much bigger. And we can also see, as we expected, this test is the least useful, has leaves. And that makes sense because it doesn't separate the data. So now we can start building a greedy ID tree. This is a greedy algorithm, so that means it's not guaranteed to give you an optimal solution, but it's generally pretty efficient. So the greedy ID tree algorithm, or specifically a greedy disorder minimizing ID tree. Basically, we're going to keep picking tests that have the lowest disorder, until the data is fully classified or we run out of useful tests. So we'll pick the test with lowest disorder. Until training data is completely classified. Or until there are no good tests left. So in this case, we'll start with the bark texture because we said that has the lowest disorder. So we'll build an ID tree starting from bark texture. So that has 3 branches. What happens if we have glossy bark texture? What should this tree do? Yeah, classify it as oak. So any tree with glossy bark texture will be an oak based on our training data. And then similarly, any with smooth will be a maple. What happens if it has furrowed bark? Well, we'll have to check another test. I heard leaf shape. So, well, is leaf shape the best test? So that has the second lowest disorder here. But it turns out the disorder is actually going to be different in the second round, or it might be different because we're looking at a different subset of the data because we no longer care about separating out these points that have glossy bark or smooth bark because we've already classified them. So we're going to recalculate the disorder for the tests that might still be useful. So we already decided has leaves won't be useful, so we won't bother with that. But we can try orange foliage and leaf shape. So orange foliage has yes and no. So it's often helpful if you cross out the points in your training data that are already classified. So in this case, we would cross out the first oak and the last 2 maples because they've already been classified, so we don't need to separate them anymore. So now we're just looking at the second and third oaks and the first maple. So what would we have in our yes branch for orange foliage? Yeah, so we have 2 maples there. And then for no, it looks like we have 1 oak. What's the disorder of this test? What's the disorder of each of the branches?
Should be the other way around.
Is that backward?
1 maple, 2 oak.
Yeah. 1 maple, 2 oaks. Good call. The disorder is still the same, though. So what's the disorder of this test? 0. Because this branch is perfectly homogeneous and that one's perfectly homogeneous. So we have a disorder of 0 there. And so we can try leaf shape just to see if we can get a better disorder. Disorder will never be negative, but maybe they'll both be equally good. So leaf shape, we have pointy and rounded. What would be in the pointy branch? 1 oak and 1 maple. And then in the rounded branch, we have 1 oak. So whatever this disorder is, it's going to be greater than 0. And you could calculate it to figure out exactly what it is. So which test do we want to use next? Orange foliage, yeah. So we'll put that into our tree. So notice that in this case, the second best test in the first round was not the same as the best test in the second round. And sometimes it will be, other times it won't be. It depends on the data. So now we have a yes branch and a no branch. What happens if it's yes? Maple. And otherwise it'll be oak. So in this case, we've perfectly classified all of our training data so we can stop adding tests. So now let's see how we would use this tree to classify unknown points. So let's say that we have some new training point, some new test point. We go outside and we find a tree and we discover that it has Gesundheit. We can discover it has furrowed bark, and it does have orange foliage, and it has pointy leaf shape. How would we classify it? Maple, because we're going to go down this tree and we'll go, what's the bark texture? It's furrowed, so we'll go down this branch. Does it have orange foliage? Yes, so we'll go down this branch and we would classify it as a maple. Does it matter that it had pointy leaves? No, because in this case we decided that we're not using the leaf shape test, so it doesn't matter what shape leaves it has, we're not using that. Okay, so one other thing that we might want to do with ID trees is numeric tests. So we're going to go back to this example with the rock data. And on the handout there's an ID tree drawn. And we're going to see how we would draw the boundaries on this graph corresponding to that ID tree. So the tree starts with density greater than 3, and then has hardness greater than 4.5 and hardness greater than 3.5. Is that correct? Okay, so how would we represent this density greater than 3 test on a graph? Yeah, draw a line. So this is, we can represent this density, in this case is the y-axis, so we can just draw a horizontal line for density greater than 3. And then how do we represent the hardness greater than 4.5? Yeah, so we'll have a vertical line. Does it go all the way? Like, should the line go all the way from the top to the bottom?
No.
Why not?
Because if the classification doesn't go past the...
Yeah, because we're only in one branch of this tree. So we're only considering the points that have density greater than 3. So this line will not actually go into the bottom half of the graph. It only affects the top half. And then similarly for hardness greater than 3.5, that would be right there. So that's how you can draw ID tree boundaries on a numeric graph. Another question you might ask is, how did we come up with these tests? In this case, it was given, but in general, if you were looking for numeric tests, you might want to choose the midpoint between some features. So like density greater than 3 is a better test than, say, density greater than 2.1, because there's more space between the features. Okay, are there any questions on any of this? Yeah.
Well, is it ever possible to have two vertical lines in the same classification point, like hardness greater than 4.5 and hardness 3.5 in the same
Like if there was another one right here or something?
Yeah.
Yeah, definitely. So if this was some fourth type of rock, say rock type R, then we would definitely want some sort of test to separate that from the other things.
Okay. There's
also, I don't remember which quiz, I think it's 2013 quiz 2 maybe. There's a numeric ID tree problem, I think it is 2013, where you end up with actually a whole bunch of lines even separating points of the same type just because of the way the tree works out. So that might be a good thing to look at. Yeah?
Why is there a negative outside the summation?
That negative? So that's because this log the log of a fraction is negative. So the negative sign is just to result in a positive number so that we get disorder going from 0 and up instead of negative numbers.